Hi, I am Kaden. I am from class PE04 and here is my explanation on the medical electronics video project. This is my patch circuit, which is a biosignal processing circuit. It will be connected in between a microphone and a speaker. So let's take a look at the block diagram of this circuit to get a better understanding. The whole idea of this circuit is to allow biosignals, such as heartbeats, to be detected by the microphone and then broadcasted by the speaker so that it can be heard easily. What the biosignal processing circuit does is that it will be able to detect the biosignal, which is known as signal acquisition, and then it will process the input. There are three main parts to processing the input: the preamplifier, the low-pass filter, and the audio power amplifier. I will roughly explain each part before going into detail later on in the video. So, firstly, the preamplifier helps to amplify weak and noisy signals. Since biosignals are generally very small, usually in the millivolts range, and are often buried in noise, this stage is very important as a base for this circuit. Next, the low-pass filter helps to block high-frequency noise while allowing low-frequency signals to pass through, since most biosignals are low-frequency. Lastly, the power amplifier increases the signal's current to be driven into the speaker. Here is the schematic of the circuit. Once again for reference, here are the three main parts of the circuit. For the first stage, IC1A is one op-amp from a TL072. The TL072 is a dual low noise JFET input general purpose op-amp. It sounds like a mouthful, but really what it's trying to say is that op-amp is referring to operational amplifier, JFET means junction field effect transistor, and dual simply means that there are two op-amps within the IC. The op-amp is operating on single supply mode, since one supply voltage is connected to VCC, while the other is connected to ground. This op-amp supplies a voltage gain, somewhere between 10 mV to 1 volt. Before the op-amp, there is a voltage divider consisting of R5 and R6, as well as an electrolytic capacitor C1 connected at the non-inverting input of the op-amp. C1 is a coupling capacitor, meaning it blocks DC voltage while allowing AC to pass through. This is important as it allows the biosignal, which is AC, to get transferred to the next stage, while any DC bias or offset value will not affect the next stage. The voltage divider of R5 and R6 provides half of the supply voltage, allowing it to work in single supply mode. Since VCC is 9 volts in this case, the voltage divider will provide 4.5 volts. This is important since the op-amp is working in single supply mode. This means that the negative sides of the waveform will be cut, and this is where the 4.5 DC offset will come in handy, as it will shift the entire waveform upwards, making sure no part of the waveform is cut. C4 is located at the output of the op-amp, and it has the same function as C1. Because the amplifier will amplify both AC and DC, C4 is needed to prevent any DC offset so that it will not affect the next stage, but it will keep amplified AC output. Looking at the configuration of the first stage, it is a closed-loop non-inverting amplifier. It uses the formula 1 plus RF over RI, F referring to feedback resistor while I referring to input resistor. In this case, RF is R2 while RI is R3. Hence, the passband gain of this stage would be 1 plus 220 kilo ohms over 10k ohms, and it will give the voltage gain of 23. For this circuit, since we're using 200 mV peak to peak to represent the biosignal, we can multiply this voltage by the voltage gain of 23 to obtain an expected output of around 4.6 volts. R2 and C2 make a low-pass filter, while R3 and C3 make a high-pass filter. Together, they are combined in series to make the bandpass filter. A bandpass filter only allows a specific frequency range to pass through. To elaborate further on the previous sentence, let's take a look at this table here. We can see that as the frequency increases, the gain also increases until around 100 Hz, whereby the gain is 22.5, which is actually very close to the calculated gain previously mentioned of 23. Any frequencies higher than its cutoff frequency will result in the gain dropping. After plotting this data onto a semi-log graph showing the frequency response curve, we can see that the 27 decibels is the pass band. We can draw a line 3 decibels below the band and show the cutoff frequencies. From my graph, the high cutoff frequency is 1400 Hz and the low frequency is 20 Hz. This results in a bandwidth of 1380 Hz, which is basically 1400 Hz minus 20 Hz. Before we take a look at the oscilloscope, let's first take a look at how the power supplies are connected. The top red and black wires are connected to the DC power supply and are connected to the power rails of the breadboard. The bottom red and black wires are connected to the function generator and are connected to the positive for C1 and ground. For stage 1, I set up the DC power supply to 9 volts, as shown over here, and the function generator to 1 kHz 200 mV peak-to-peak sine wave. The oscilloscope cable channel 1 is connected to TP1, measuring the input voltage, and the oscilloscope of channel 2 is connected to the TP2, which is showing the output voltage. As you can see, the yellow graph has a VPP of 200 mV peak-to-peak, while the purple graph has a VPP of 3.32 volts, which is very similar to the voltage shown under the Vout column for the table. I then slowly adjust the frequency, and you can see that the peak-to-peak voltage of the purple graph decreases, which proves my explanation early on about the higher the frequency after the cutoff frequency, the lower the voltage due to the decreasing voltage gain. For the second stage, IC1B is using the second op-amp from the same IC TL072, which was used for IC1A. Once again, there is a voltage divider which acts as a level shifter so that the output will not be clipped. This amplifier has a negative feedback loop. More specifically, it is a closed-loop inverting amplifier. The terms negative feedback and inverting mean that a portion of the output of this op-amp will be fed back into the input and will be 180 degrees out of phase due to it being an inverting amplifier. The formula for an inverting amplifier is negative RF over RI, whereby P1 is RF and R4 is RI for this circuit. Notice how RF is a trimmer. This means that the gain for this amplifier can vary based on the resistance set by this trimmer. A larger resistance from the trimmer will result in a larger voltage gain. The gain can be carefully adjusted such that it will function as a linear amplifier and not saturate the output voltage. To set up stage 2, I left the DC power supply and function generator untouched and did not change any values. However, I now adjusted the oscilloscope cable connected to channel 2 to TP3 instead, which is located at pin 7 of the IC. After turning on the power supply and function generator, you can then see on the oscilloscope how the waveform is being affected by the trimmer resistance, since I am adjusting the screwdriver which adjusts the resistance and affects the voltage gain. Notice when I turn it clockwise, the amplitude of the graph increases, since the voltage increases with increasing resistance. After a certain point in trimming, you will notice that the peak and trough of the waveform begin to flatten. This is what I meant by clipping. The graph becomes saturated after a certain voltage gain, which results in it being cut off. From this, you can see that the expected output waveform should be around 6 volts without clipping. In this video, I'm showing just the oscilloscope for a clearer view as to how the waveform changes when adjusted by the trimmer. Also, do take note that the second stage is an inverting amplifier, hence the output is 180 degrees out of phase. For stage 3, we see yet again more coupling capacitors C5 and C8, and another voltage divider consisting of R11 and R12. Once again, C5 and C8 will block any DC input while allowing AC to pass through, and the voltage divider allows the op-amp to work in single supply mode and acts as a level shifter for the op-amp. The IC2A is a second TL072 IC used. Looking at the configuration of the stage, it is patched as a Sallen-Key second-order low-pass filter. It is second order since it is made of two low-pass RC networks. The Sallen-Key is a low-pass filter, meaning it will allow low frequencies to pass through while blocking high frequencies. You can tell that it is patched as a low-pass filter since capacitors C6 and C7 are bypass capacitors, which are connected to ground. What this means is that high frequencies are passed through the bypass capacitors into ground. It is also an active filter since it has an op-amp, which will provide voltage gain on top of being a filter. Since there is no RF and RGD in this Sallen key, RF referring to feedback resistor and RGD referring to ground resistor, it has unity gain, meaning a voltage gain of 1. Capacitor C7 provides feedback to help shape the response near the edge of the passband. Since the lowest frequency possible is 0 Hz, the bandwidth of this filter is determined by the cutoff frequency, which can be calculated using this formula. Using the values in the schematic, the cutoff frequency is about 1 kHz. This table shows how the Sallen key operates by itself, whereby it is not connected to the first two stages of the circuit. It is shown that when the frequency is below 500 Hz, the filter is at unity gain, as explained earlier. However, any frequencies higher than that results in the gain and output voltage dropping. This is known as signal attenuation, whereby any frequencies after the cutoff frequency results in a weaker output due to a smaller voltage gain. Using the data to plot the frequency response curve on the semi-log graph paper, we can draw a -3 decibel line to determine the cutoff frequency, which is about 950 Hz in my case, and is close to the expected bandwidth, which was calculated earlier on. Moving on to the oscilloscope, I will first show the waveform when the Sallen key operates by itself. As you can see, I disconnected the green wire such that stage 1 and 2 do not connect to the Sallen key. After adjusting the function generator to be at 10 Hz, 5 volts peak-to-peak sine wave, but keeping the DC power supply untouched, you can see that the waveform has a peak-to-peak of 4.88 volts, which is actually very close to the 5 volts, since any frequency below 500 Hz results in the filter having unity gain. However, as I begin to increase the frequency, you will notice that the peak-to-peak voltage begins to drop. Now, when I connect the green wire back and connect the second oscilloscope cable to TP4, I use 1 kHz 200 mV peak-to-peak sine wave for the function generator and keep the DC power supply untouched. This gives me a peak-to-peak voltage of 2.53 volts due to the fact that around 1 kHz is the cutoff frequency. After changing the frequency to 200 Hz, which is below 500 Hz, I get an output of 5.44 volts, which is very similar to the output voltage we got at stage 2 before saturation. So if you're wondering, yes, the trimmer from stage 2 will also be able to adjust the waveform at TP4. In this final stage, the IC used is a LM386N-1. It is an audio power amplifier that drives a speaker. Internally, it is designed to work in single supply mode, so no voltage divider is needed in this stage, unlike the rest of the amplifiers used. Another important point, this amplifier is the only amplifier in the entire circuit that drives current that will power up the speaker. The input first enters trimmer P2, whereby pin E has full amplitude while A and S have zero amplitude of the input waveform. Capacitor C15 and resistor R17 filter out high frequencies at about 40 kHz and above. This is known as a Zobel network, and its role is to keep the output waveform stable. Once again, C13 is a capacitor that will block out DC signals while allowing AC to pass through. For this first video, I'm setting the function generator at 1 kHz 200 mV peak-to-peak sine wave. I then use the trimmer to control the output waveform at test point 5, which is connected to the second channel of the oscilloscope. The output voltage obtained here is around 7.76 without saturation of the sine wave. Now, I adjust the frequency to 200 Hz, but I keep the amplitude, and same thing, I adjust the trimmers such that I get the correct output voltage. To recap, All the theoretical expected output voltages we calculated at each stage of the circuit were actually very similar to the output voltages we obtained on the purple waveform of the oscilloscope. This means that the circuit was functioning well and working. In summary, I just explained how a biosignal will be processed and amplified by the circuit. It is a really neat system since it uses filters to make sure that the output waveform is clean and undistorted, and it uses amplifiers to drive sufficient voltage and current into the speaker such that we get a nice acoustic output, which simply means the sound energy from the speaker which we will be able to hear clearly. If we simply took the biosignal, which was around 200 mV in the oscilloscope demonstration, and drove that into the speaker, which usually has a resistance of 8 ohms for example, the power will only be about 5 mW, since power is equal to V squared over R. Hence, we will use the signal processing circuit, giving us about 8 volts at the output, which will result in a power of 8 watts, which is definitely suitable for an acoustic output. As a student, I simply just patched up the circuit and managed to get the output, which were the waveforms shown on the oscilloscope, and it matches the theory explained for each stage. However, how can we actually apply this circuit to real-life problems or devices? The most common application is in electronic stethoscopes, which help to amplify heartbeats to be easily heard by doctors. The circuit can also be used for continuous patient monitoring, since patients in the intensive care unit will need real-time monitoring of their heart rhythm. Since we're on the topic of amplification, a similar circuit can also be used in hearing aids or medical hearing devices, whereby signal strength and clarity is very important. Now, let me quickly talk about my experience troubleshooting this project. My experience patching this circuit was generally fine, except for a few patching mistakes made in stage 1 of the circuit. In addition, the oscilloscope wires on the table are a bit messy, and which channel that goes to which test point of the circuit was not clearly indicated. Hence, one way I can improve is by laying out the wires on the oscilloscope neater in the future, such that it will be more visible as to how the oscilloscope is connected to my circuit. In addition, I could try to switch up the connection of the first oscilloscope cable. It was constantly connected to TP1 to prove that the biosignal, which was represented by the function generator, was kept constant and my circuit was fully functioning. But it would be good to change the connection to the previous stage, such that we can see the change from the input to the output from stage to stage clearly. That's all I have to share for this video project. Thank you for listening to my explanation on the biosignal processing circuit, and I hope you have a better understanding of how it works now.